Okay, folks, let's talk about state space, what it is, and talk about an overview of it. Okay, so if you have a second order differential equation, well, let's do first order. If you have a first order differential equation, something like this, putting this system into state space is pretty trivial, solely because the way state space works is you're trying to put the system into the form x dot equals ax plus bu, where in this case we're doing CISO systems, so that's single input, single output. So u is going to be a scalar, a single input, and then you might think that x is our output, but we're actually going to have an output equation, cx plus du, like this, and so y is actually our output. So if we drew a control block diagram, we would have u, our input, g would be our in this case, g could be a transfer function, or it could be a state space system, and our output would be y in this case, okay? Typically in systems that you do in academia, c is a, what's the word I'm looking for, is identity, and so y would be equal to x. Or not identity, actually it would be equal to like 1, 0, and you would just pull out the first variable, but that's not necessarily a big deal. So if you wanted to get this system into this form, right, you would just do x dot equals negative 4x plus, and I'm going to put a 1 here just to show you that this is your A matrix, it's a scalar, and this is your B matrix, it's also a scalar. And then your output equation would be 1x plus 0u, and so C would be 1 and D would be 0. And this would be your state space system. So for first order systems, state space seems pretty trivial, okay? But let's talk about what would happen if you get into a second order system. So say you have x double dot plus 4x dot plus 3x equals u. Well, now getting it into this form is not so trivial. And so what you do is, if you look at the size of these matrices, this matrix is a 1 by 1, this is a 1 by 1, this is a 1 by 1, and this is a 1 by 1. And that's because this system was a scalar. When you have a 2 by 2 system, when you have a second order system, your A matrix is 2 by 2, your B matrix is 2 by 1, your C matrix is 1 by 2, and your D matrix is 1 by 1. Your D matrix in this case is always 1 by 1 because it's a single input, single output system. But you see the number of rows and columns is dictated by the order of your system. So in this case, what you're going to do is you're going to write a 2 by 1, that's your state vector. Your A matrix is a 2 by 2. You're also going to have your state vector over here. You're going to have your B matrix, and you're going to have U, okay? So what you want to do is you need to figure out, this is x dot equals ax plus bu, okay? There it is right there. You just need to figure out how to fill this in. Well, so how do you fill out your state vector here? Well, what you do is you just take your lowest power of x and then take a derivative, okay? And there you go, there's your state vector. How do you get x dot? Well, you just take a derivative of x, so that's x dot. Derivative of x dot is x double dot, okay? So now how do you fill this in? Well, I have an x dot here and I have an x dot here. So if I look at this, x dot is equal to 0 times x plus 1 times x dot plus 0 times u. So 0 times x, 1 times x dot, 0 times u. You basically did the same thing. Your x double dot equation, all you need to do is just rearrange this equation, and you're going to get x double dot is negative 4x dot minus 3x plus u. So that means there is a negative 3 times x, a negative 4 times x dot, and a 1 times a u. Pretty simple, okay? And there's your system in state space, okay? So I'm going to take a picture of this and then move on and say, okay, well, Big Whoop, what is the appeal of this? And actually, I could write this in this corner here. The whole point of state space is the fact that, first off, if you have a second order, notice that this equation here, this is x dot equals ax plus bu, and then y equals cx plus du, right? Even though this is a scalar, the state space equations are the same. Over here, oh, and we forgot to write y. Y needs to equal 1, 0, x dot plus 0, u. Because y equals 1 times x, 0 times x dot. Because you want y to equal x. And so there's your C matrix and there's your D matrix. If you look at these equations for a second order system or a first order system, you have the exact same state space equations, which is really nice. Because it means that your solution, let's say u equals 0, it means that x dot equals ax, which means that x dot minus ax equals 0, and that is a homogeneous equation. It has no forcing input. And what this means is that x as a function of time is equal to your initial conditions times e to the at, where this is the matrix exponential. Now, how do you do the matrix exponential by hand? It's really hard. You have to do eigenvalue decomposition, you have to multiply and invert matrices. It's extremely difficult to do. But guess what? Computers were invented, and it's very, very simple to do the matrix exponential on computers. So you have a situation where you could have, say, helicopter dynamics, which is a 42-state system, right? You're in academia, you're just dealing with 2 states, spring, mass, damper. If you go out into the real world, you could be given the state space dynamics of an F-16, where it has 12 or 18 states, or a helicopter that's 42 states, and you have a 42 by 42 matrix. But the computer doesn't care. The computer it'll run slower, but all it has to do is just compute the matrix exponential, and you're done. Okay, so that's what's really, really nice about state space. Okay, so then let's talk about 2 more fundamentals, and then we'll get into PID control. So let me scan this in. Oop, gotta switch to beacons. Okay, so while that's scanning, I'm going to erase the board here. Okay. And let's now talk about going from transfer functions to state space. So let's say you have a transfer function g, which is big X over big U. And I'm going to take the simple approach where the numerator is, say, 10 over s squared plus 2s plus 4. And what I want to do is I want to put this in state space. Well, if you did this the long way, what you could do is you could multiply this and get big X s squared plus 2s plus 4 is equal to 10u. And then you could take the inverse Laplace of this, and s squared, right, is x double dot in the time domain. S in the time domain is x dot, and then x in the time domain is just x, and then capital U in the time domain is just 10u. So then your state space would just be exactly how it was before, except you have different numbers here. 0, 1, that's always the same. X dot. 0, 1, that's always the same. Your bottom row is going to be a -2 times x dot and a -4 times x. And if you look here, this 4 and this 2 are exactly the same as this transfer function here. Now I'm going to give you a moment, pause your YouTube video, go through this derivation on your own. I did that super fast, but this is a YouTube video. You have pause, you have rewind, you have comments. So post in there and ask me comments if you have questions. Okay, so that's transfer function to state space. So then what happens if you want to go backwards, right? Well, if you want to go backwards, let's take your state space system, ax plus bu, and let's take a look at your equations, cx plus du. Well, let's take a Laplace transform of this. I'm going to get big X s equals a big X plus b big U. And then I'm going to get big X si minus a equals bu. And so then if I want to divide by u and then multiply this on the right, and I'm going to get g is big X over big U, that's si minus a inverse times b. And so again, si minus a is pretty difficult to do by hand if it's a big system, but computers don't care, okay? Now, let's actually do this si minus a for a moment for this problem, and let's see what we get. And you'll see that we'll actually get something kind of interesting. So if I take s times identity, right, so s times the identity matrix, minus the A matrix, so minus, remember this is the A matrix, 0, 1, negative 4, negative 2, equals, I'm going to get, let's see, S minus 0, 0 minus 1, 0 minus minus 4, S minus minus 2, so I'm going to get S plus 2. And then I need to take the inverse of this, okay? And so, how do you take the inverse of a matrix? Well, first you have to divide by the determinant, and then you multiply it by the adjoint matrix. And so the determinant, is the cross product, so you're going to get S times S plus 2, not the cross product, it's the cross. S times S plus 2 minus 1 times 4. And so you get S squared plus 2S plus 4. That is your determinant. And look at this. The determinant of your state space, the determinant of Si minus A, is the same thing as your characteristic polynomial. So what that means is the eigenvalues of your A matrix are equal to the poles of your transfer function. And so what that means is if someone gives you a state space system, all you need to do is compute the eigenvalues of your A matrix, and that will tell you the poles. So if the real part of the eigenvalues of your state matrix are less than equal to 0, strictly less than 0, it means the real part of your poles are less than 0, which means your system is stable. So if you're given a state space system and the question says, is this system stable? All you need to do is compute the eigenvalues of the matrix, and if the real part of those eigenvalues are less than 0, you're stable. That's all you need to do because of this property here. And again, pause the video, go back, and make sure you understand this derivation. Okay? So I still haven't completely computed the transfer function, right? So I just computed the determinant, right? So the inverse of Si minus A is equal to the adjoint matrix of Si minus A over the determinant of Si minus A. Okay? So the adjoint matrix is you swap these and negate the off diagonal. And so what you're going to get is, I'm running out of room here. Let me just take a screenshot of this real quick. Okay. So I'm going to erase this up here and this over here. I still want the determinant. Okay, so I want the adjoint matrix. So the adjoint matrix of Si minus A is, you swap these two and you negate the off diagonal. Okay? And then the inverse then of Si minus A is the adjoint, so it's S plus 2, 1, negative 4S all over the determinant, S squared plus 2S plus 4. And then you multiply this by, I have an error here. This is 10. 10U, that's 10. I'm sorry. So if you pause the video and you got an error, and you came back and you were like, wait, where'd the 10 go? There's the 10. I apologize. So there's the 10. So negative 2 x dot, negative 4x, 10u. So this is actually 0, 10. Okay? And if you look at this, remember, I'm sorry. This is the inverse of Si minus A. The transfer function g is Si minus A inverse times b. So if I put a b here and a 0, 10 here, and I multiply this out, g is going to be 1 over s squared plus 2s plus 4 times, you're going to get s plus 2 times 0 plus 10, and then you're going to get negative 4 times 0 plus 10s. Now, why do I have a matrix? Well, remember, G is big X over big U, but over here, we assumed that X was a scalar. Down here, X is actually a vector. And remember, X, so I'm going to draw a vector here to denote that this is a vector and that's a scalar. X in the time domain is little x dot. So 10 over 1 over s squared plus 2s plus 4 is the transfer function of x over u. 10s over s squared plus 2s plus 4 is the transfer function of x dot. And it's pretty clear that the x dot comes from this s here. And so there you go. So takeaways. So you have your equations of motion, you solve for x double dot, and that can put your system into state space. The eigenvalues of your A matrix give you the poles of your transfer function, which determines stability. If you want to convert from transfer function to state space, you can just multiply it out. If you have numerator dynamics, you have to do something else to it, but I'm not going to go over that in this video. If you have a state space system and you want to go to transfer function, you can use this equation here, SI minus A inverse B. If you have a system that's bigger than a 3x3 and you can't do the inverse by hand, you can use a computer to do state space to transfer function. And then finally, what I want to go through today is, actually I think I'm going to save that for another video and talk about feedback control of state space. So the only takeaways of this are going from equations of motion to transfer function to state space and being able to draw conclusions between the three. You have, for equations of motion, you have your characteristic polynomial, which determines stability. For your transfer function, you have your roots of your denominator, which determines stability. And then for state space now, you have the eigenvalues of your A matrix determine stability. And so all of those three things are all related to one another, and they help you determine stability of the system. Okay? In the next video, I'll talk about PD control of state space.